Hello and welcome to lecture 36 of analog integrated circuit design. We have been looking at op-amp topologies and how to improve the DC gain, and so far we investigated a couple of topologies that increase the DC gain by increasing the output resistance of the transconductor. Such an approach is not useful when we have a resistive load, because the total output conductance will be dominated by the load, and for a given transconductance we will only have a given DC gain. To increase the DC gain, we will have to increase the transconductance, and this enormously increases the power dissipation. Okay. So, we have to go to multi-stage topologies, which inherently give you a lot higher DC gain even with resistive loads. So, that is what we will discuss in this lecture. When discussing the op-amp at the control source level, this was the basic op-amp. Now, we said that the problem is the output conductance of this transconductor. To obtain a better I to V conversion, the problem here is not all of the output current of the transconductor goes into the capacitor, some of it goes into this G out. To do better, we use a current controlled voltage source using a feedback circuit. Okay. The advantage here is that because of feedback, the input node is at a small voltage. So, the current that goes through G out is quite small. Okay. Most of the current ends up going into the capacitor C. So, this is a much better integrator than this one, and of course, the transconductor that we use for the current controlled voltage source also will have an output resistance G02. So, this topology we saw that has a higher DC gain. The circuit on the left side has a DC gain of GM1 by G01, and the circuit on the right side has a DC gain of GM1 by G01 times GM2 by GO2. Okay. And both of these integrators have the same unity gain frequency GM1 by C. Now, we also analyze this in great detail. When we have this capacitance C1 and a load CL, we saw what happens. So, we end up with 2 poles and a 0, and we also evaluated the conditions under which we get sufficient phase margin, etc., etc. Okay. So, we know that for instance, the non-dominant pole is at approximately at minus GM2 by CL plus C1. Because GM2 is in feedback, we get a more complicated expression. I am going to write that soon. So, we have all the things that we need to understand this topology. Okay. All we have to do is to implement this at the transistor level. Now, how do we go about doing it? First of all, you see that the input part of it is the same as before. Okay. We have a transconductance which was driving a capacitor, now it drives a current controlled voltage source. We have already spent some effort coming up with topologies for this. So, we will use our single stage op amps for the transconductor. A single stage op amp is nothing but a transconductor, and that we will use in place of GM1. Now, we have to realize this transconductance GM2 and connect the integrating capacitor across it, that we will see how to do and complete the circuit. Okay. So, basically GM1 will be made by using the differential pair transconductor. Okay. This is what we had and this is GM1. We know that if we have V bias plus Vd by 2 and V bias minus Vd by 2, there is a current GM1 Vd that tends to flow out if there is some proper termination on this side. Okay. Now, what do we need here? We need another transconductor, okay, voltage controlled current source around which we connect the integrating capacitor. Now, what is the transconductor that we need to use here? There is a variety of choices, but we will try to use the simplest that is possible, and we recognize that a transistor by itself is a voltage controlled current source or a transconductor. Okay. A common source amplifier, for instance, is nothing but a voltage controlled current source loaded by a load resistor. Okay. So, that is what we will use. Now, we can use either PMOS or NMOS transistor. We know that the quiescent output voltage here is VDD minus VSG 3. Okay. So, typically especially for large values of VDD, this is lot closer to VDD than to ground. Now, let us say you want to have a PMOS common source amplifier or a PMOS transconductor biased at some current I2, let us say. Okay. Then the gate needs to be biased at VDD minus VT minus VD sat corresponding to a current I2. Instead, if you had an NMOS transistor, biased at let us say the same current I2, the voltage would have to be Vt, the threshold voltage, plus Vd sat at a current of I2. Now, you see that the output voltage of the first stage is lot more suitable for biasing a PMOS transistor than an NMOS transistor. Okay. If VDD minus VSG3 has to be equal to Vt plus Vd sat, there is some constraint between VDD, VSG3, Vt and so on. Okay. On the contrary, if you want to make this equal to VDD minus Vt minus Vd sat, VSG3 has to be equal to Vt plus Vd sat. Okay, and VSG3 itself is the threshold voltage of the PMOS transistor plus some overdrive. So, all we need is to have the same overdrive for this transistor as well as that transistor, and the entire circuit will get biased. Okay. So, it is a lot easier to interface a PMOS stage to a NMOS differential pair compared to an NMOS second stage. Okay. So, for this reason we will use a PMOS second stage with an NMOS first stage, that is NMOS differential pair first stage. Now, the other topology is also possible. You can use an NMOS second stage with an NMOS differential pair, and that is sometimes used when the supply voltage is very low and you can satisfy these constraints, but usually an NMOS differential pair will be followed by a PMOS common source amplifier. I say common source amplifier, what it is really is a voltage controlled current source that we will use as an amplifier. Okay. So, my second stage GM will be that, and I would want as high a DC gain as possible in this as well. So, I will not load it by a resistive load, I will load it by an active current source load. Okay. Let me call this M11 and this is M12. Okay. I can connect it like that, and the gate of M12 is biased from a current mirror. I will assume that the bias is derived from the same place that we derive the bias of M0 from. Okay. By adjusting the size of M12 compared to M0 and the diode connected transistor, we can get any current that we want here. Okay. Now, this is GM2, this is GM1. The first stage is a differential pair, because we also have to take the difference between the desired and the actual quantities, that is done in the first stage, that is why it is a differential GM. The second stage is simply a single ended one, because it has to take the output of the first stage. Okay. Now, across this we need to connect the capacitor C, this is the integrating capacitor C, and we are done. Okay. If this is the output, this is the positive input and that is the negative input. That is obvious from these polarities. This is negative and that is negative. So, the gain from there to the output is positive. Okay. So, this is our two stage op amp. If you recall, it was also called the Miller compensated op amp. Okay. Now, we already know the small signal parameters of such a topology. Okay. Let me put this down again. I will show only the output conductance, but if there is a load resistance, that can be absorbed into the output conductance GO2. This is GM1. Okay. Now, what is the transfer function that we had for this? For V0 divided by the difference voltage Vd or the error voltage Ve. We had the DC gain GM1, GM2 by GO1, GO2, and we had a right half plane 0, and we had a second order denominator, which we approximately resolved into two first order factors, S by P1 and S by P2. Okay. And the 0 Z1 is at GM2 by C, pole P1 is at GO1 by, it is approximately at GO1 by C1 plus C times GM2 by GO2 plus 1. There were some other terms which we can neglect, and the second pole is approximately at GM2 with this feedback fraction C by C plus C1 plus GO2 divided by CL plus the series combination of C and C1. Okay. So, we know all of these things. We have to find this for our transistor level op amp. So, the first thing we need to do is to simply identify the values of these different components C1, CL and C that we already know, G01, G02, etc. And also one more thing to keep in mind is that in this block diagram we have assumed GM1 to be an ideal transconductor. In reality, we know that from our analysis of the simple differential pair, between the input voltages here, let us say I apply plus V d by 2 and minus V d by 2, and the output current that is coming out of the first stage transconductor, there is a pole and a 0, that is because of the mirroring. Okay. So, this GM1 has to be replaced by YM1, okay, which is the transadmittance that includes the pole and the 0. So, if we do all of that, we will get the frequency response of our Miller compensated 2 stage op amp at the transistor level. Okay. Let me copy over this picture. So, first of all, what is C1? C1 is the total capacitance at the output of the first stage, okay, and that consists of parasitic capacitances from every transistor that is connected there, M4, M2 and M11. As usual, I will neglect the values of CGDs because the transistors are operating in saturation region. So, C1 will be CDB4 plus CDB2 plus CGS 11. Okay. So, that is what we have, this one, that one and that one. Remember, VDD is small signal ground. Similarly, what is CL? Okay, the total CL will be whatever load capacitance we connect, CL prime, plus the parasitic capacitances due to M11 and M12. So, we do not usually calculate all these exact values by hand, we resort to the simulator, but we need to know how each of those values influences the total capacitance or the total parameter, and which consequently affects the pole value. Okay. Now, what is GO1? GO1 is the output resistance of the first stage, and that will be equal to GDS1 plus GDS3. This again we have evaluated, and GO2, that is the total conductance at the output of the second stage, will be GDS11, which is due to this transistor M11, and GDS12 due to the current source transistor M12. Okay. Whenever you bias something with a current source, the current source contributes an incremental resistance which appears in parallel. Okay. Now, if we have a load resistance RL, to easily get the results, we simply absorb that into the total conductance at the output of the second stage. Okay. The value of C, the integrating capacitor, is known. So, everything is known, and also the transadmittance of the first stage is nothing but the DC transconductance of the first stage times 1 plus S CD3 by 2 GM3 divided by 1 plus S CD3 by GM3. As we found out while discussing the single stage op amp, there is a parasitic capacitance CD3 here contributed by M1, M3 and M4, and because it acts on only half of the current, we get a pole and a 0. Okay. So, the total transfer function will consist of not this GM1, but YM1, which has a pole and a 0, and the 2 poles here and the 0 over there. Okay. So, all we have to do is to substitute the terms and find out what each of these things is. The DC gain is the product of the DC gains of the 2 stages, which is GM1 by GDS1 plus GDS3 times GM11. Remember, GM11 is GM2. Okay, I will write that down as well. GM2 is nothing but GM11, the transconductance of this stage. GM11 by GDS11 plus GDS12, and the unity gain frequency should be GM1 by C. Okay, this is what we have calculated, and we will place the non-dominant poles and zeros beyond the unity gain frequency. Now, the non-dominant pole that we have calculated is minus GM11 C by C plus C1. C1 value can be substituted from the expressions over here, okay, plus the total output conductance GO2, whatever that is, usually that is negligible, series combination of C and C1 plus the total CL. This is one of the non-dominant poles. In addition to this, we also have the non-dominant pole due to the first stage, which is GM3 by CD3. Okay. Of course, it is in the left half plane, and there is a right half plane 0 that we are quite familiar with from our earlier analysis, and that is at GM11 by C. There is also a left half plane 0 due to the first stage, which is at minus 2 times GM3 by CD3. Okay. So, overall we have a dominant pole which is very close to the origin of and we have these non-dominant poles and zeros. We have 2 non-dominant poles and 2 non-dominant zeros, okay, and we should position these so that our phase margin is a healthy value of, let us say, 45 degrees or 60 degrees or whatever we desire. Okay. Now, a couple of things. First of all, these expressions are general, and any external load that you have, either load resistance or load capacitance, can be absorbed into these things. Okay. All you have to do is to manipulate the value of CL or GO2. Now, what happens to the DC gain? Why is this better for a resistive load compared to the single stage op amps? When we have resistive load, it is only the DC gain of the second stage that is affected. Okay. The first stage gain is not affected. Now, we can afford to have a low gain in the second stage, because we have 2 stages of gain. Let us say the second stage is designed for a modest gain of only 10 or even 5, and we get the bulk of our gain from the first stage. So, this way, even with a very heavy resistive load, we can get a high DC gain without increasing the transconductance significantly. Okay. What I mean is, let us say I want a DC gain of 1000. Okay. Now, let us say my load resistance is 1 kilo ohm, or equivalently the load conductance is 1 millisiemens. If I tried this with a single stage op amp, the transconductance would have to be 1000 millisiemens or 1 Siemen. Okay. This is with a single stage op amp. Now, let us say we partition this into 100 from the first stage and 10 from the second stage. Okay. So, again we have the same RL and GL, which is 1 millisiemens. Since the second stage has to offer a gain of only 10, my GM2 can be 10 millisiemens, okay, and my GM1 can be any value that I want, because I have to adjust the value of GM1 by GO1, which is independent of the load, to be equal to 100. Okay. I do not know what GM1 is going to be, but from stability considerations I know that GM1 has to be significantly less than GM2. So, let us say I will say GM1 is 2 millisiemens. Okay. So, clearly in this case we have to realize a total transconductance of 12 millisiemens, and here the total is 1000 millisiemens. Okay. Now, of course, how much power we burn to realize a given transconductance depends on the topology, but just from the basics of MOS transistors we know that if you want a larger GM, you have to have larger transistors operating at higher currents. Okay. So, to get 1000 millisiemens, you have to burn significantly higher power than to get 12 millisiemens. So, it is not possible to drive resistive loads and have high gains with a single stage op amp, whereas it is quite easily possible with a 2 stage op amp. That is the reason 2 stage op amps are very popular and very widely used. Okay. Now, these summarize the small signal DC and AC performance of the op amp, and we have a higher DC gain and we have a number of parasitic poles, and we know what to do with them. We have to place them sufficiently beyond the unity loop gain frequency of whatever feedback loop we operate that in. Now, let us evaluate some other relevant parameters of this op amp, like the noise, offset, slew rate and the swing. Okay. Now, first let us consider the noise. We know that the input referred noise of the single stage op amp alone is 16/3 kT by GM1, where GM1 refers to M1 and M2, 1 plus GM3 by GM1. Okay. Now, let us say we have a two stage structure. We already know the input referred noise of the first stage, let me call it SV1, and this is GM1, GO1. Okay. One thing I will do is I will also ignore all the capacitors while calculating the input noise spectral density. So, it will be valid only for low frequencies, but that is okay, that serves usually as a good enough estimate of the noise. Now, let us say this is GM2. Now, I do not have to recalculate the noise from the first stage. So, what I will do is I will calculate the effect of the second stage either on its input or on its output. Okay. So, let us say I evaluate the second stage noise referred to its input, and as I mentioned I will remove the capacitor C. Okay. So, what happens, I will have some SV2. Okay. So, that is some voltage noises added over there. So, what will be the total input referred noise? It is quite easy to see. So, one way to do that is to simply calculate the total output noise first. From SV1 we have a gain of GM1 by GO1 times GM2 by GO2, and this is a spectral density. So, the total spectral density at the output due to SV1 will be GM1 by GO1, GM2 by GO2 squared, and due to this SV2, the input referred noise of the second stage, we will have SV2 times GM2 by GO2 squared. Okay. And the overall gain we know is GM1 by GO1 times GM2 by GO2 whole square. So, if I want to represent this effect of both these noise sources with a single input source here, what I have to do is to divide this by that one. So, I will have SV1 adding directly, that is what we expect, SV1 simply adds to the input plus SV2 GO1 by GM1 squared. Okay. As I have said many times, when you have a cascade of multiple stages, the input referred noise will be the input referred noise of the first stage plus the input referred noise of the second stage divided by square of the gain of the first stage, input referred noise of the third stage divided by square of the product of first and second stage gains, and so on. Okay. And if these gains are significant, then only the contribution from the first stage will be significant, all others will be insignificant, and that is apparent from this expression as well, because we have SV2 times GO1 by GM1 whole squared, which means that SV2 is attenuated by a large factor when it is referred to the input. GO1 by GM1 is nothing but the inverse of the DC gain of the first stage, which could be 50 or 100 or something. So, Effectively, when we calculate the input referred noise, all that matters is the noise of the transconductance GM1. Okay. The input referred noise of the two stage op amp will be exactly the same as the input referred noise of the simple single stage differential pair op amp. Okay. Any extra contributed from the second stage will be quite negligible. Okay. Now, the next thing we will consider is the input referred offset. Now, what do we mean by the offset here? Let us take the example of a unity gain follower, for instance. Now, if I apply an input, the output should exactly follow the input, but because of the offset there will be a difference between the input and the output. So, that is the offset. Okay. Now, we have already calculated the offset of the first stage, right. Now, just as with noise, any mismatch contribution from the second stage will be divided by the gain of the first stage and will not matter when referred to the input. Okay. Again, let me consider the two stage structure GM1. Let us say I have some VOS1 and we have GO1 over here and I have VOS2. Offset is by definition DC and I do not have to include any capacitors in the calculation. I have GM2 and GO2. So, VOS2 is the input referred offset of the second stage, VOS1 is the input referred offset of the first stage. So, the total offset at the output will be GM1 GM2 by GO1 GO2 times VOS1 plus GM2 by GO2 times VOS2. Now, when we refer this to a single offset source at the input, we divide this by the overall gain, which is this number. So, VOS at the input would be VOS1, because it is from the first stage it adds directly, plus GO1 by GM1 times VOS2. Okay. Just as with noise, VOS2 is divided by the gain of the first stage. So, when we compute the input referred offset, the contribution of the second stage will be quite negligible. Okay. So, again the offset of this is the same as the offset of the single stage op amp, okay, with the differential pair. That is, the random offset of the two stage Miller compensated op amp is the same as the random offset of the first stage differential pair, which is of course determined by the differential pair transistors and the load transistors. So, the random offset variance will be sigma VT12 square plus GM1 by GM3 square times sigma VT34 squared. Okay. Now, in case of the single stage op amp, that is, we are considering only this part, the operating point here was the same as the operating point there in absence of offset. That is, when the inputs are at V bias, the drain of M4 and M3 are at the same voltage by symmetry. Okay. And because of offset, it will be different, and the input referred offset can be calculated purely on the basis of random mismatch. Okay. Now, in case of the two stage op amp, let me just not show the load explicitly, but it can be there. What will be this value when the inputs are at V bias and there is perfect symmetry between two halves of the differential pair. Now, this voltage and that voltage will be the same as each other, okay, by symmetry. So, this is VDD minus VSG3 and that is VDD minus VSG3 as well. Okay. And let me call this voltage Vg0. At a voltage Vg0, M12 tends to carry a current I12 if it is in saturation region. Okay. The square law stuff holds only in saturation region, and this current I12 will be carried if it is in saturation region. Now, if you look at this, we have M11 which behaves like a current source and M12 which behaves like a current source connected together. Okay. Obviously, the current in M11 has to be equal to the current in M12. Now, can both of these be in saturation? It is possible if the voltage happens to be biased in the middle. Okay. Now, what will be the current that M11 carries if it happens to be in saturation region? So, to imagine this, perhaps first of all we are discussing DC situation, so we can neglect the capacitor. So, let us say I connect the drain of M12 to VDD and M11 to ground. Okay. In this case, these transistors will be guaranteed to be in saturation, and I have some current I12 here, which is the intended bias current for the second stage. Now, let us say with a gate voltage of VDD minus VSG3 or source gate voltage of VSG3, M11 carries some current I11. Okay. Now, what happens if we connect these two together? The current has to be the same. Okay. It does not matter what M1 tended to carry if it was in saturation and M12 tended to carry if it was in saturation. When you connect them together like this, they have to be the same. Okay. If I11 is greater than I12, that is the saturation current of M11 is more than the saturation current of M12, what happens is, let us say this voltage starts from somewhere in the middle, so that both transistors are in saturation region. A net current of I11 minus I12 will flow into the parasitic capacitance that is at the output. So, this voltage will keep on rising. Okay. And finally, M11 will reach the triode region and the current in M11 will reduce to be equal to I12. Okay. Similarly, if I11 happens to be less than I12, the voltage will fall down until M12 is in triode and ID of M12 equals I11. Okay. Now, this is visualized very easily graphically. This operates with a certain VSG3 and this operates with a certain VGS 12. Okay. And let us say the output voltage is V out. I will draw the ID VDS characteristics. Okay. Let us say that is ID. If I draw the ID VDS characteristics of M12, what I will get is the usual output characteristics of the MOS transistor. Let me show it with a very small output conductance. This is VO. VO is nothing but the VDS of M12. Okay. Now, I will also draw ID versus VO characteristics. I know that the VSD of M11 is VDD minus V naught. Okay. So, ID versus VO characteristic is nothing but ID versus VSD characteristic, but with the curve flipped around at VDD. Okay. You would have done this calculation when you are calculating characteristics of, for instance, a CMOS inverter. So, if this is VDD, VDD minus V naught is the VSD of that, and that will look something like that. Okay. So, this is what I called I12, the saturation current of M12. This is for M12. Maybe I can show this in a different color, and this is for M11, and that is I11. Okay. Now, what will be the value of V naught? It will be the point of intersection. You can clearly see that if I11 is smaller than I12, then M12 will go into triode region. Similarly, if M11's characteristic happen to be something like that, that is I11 happens to be more than I12, then M11 will go into triode region. Okay. So, one of these two will be in triode region if I11 is not equal to I12. Now, let us connect this in feedback and then see what happens. Let us say we connect this in unity feedback. Okay. Now, here we are talking about a case where there is no mismatch between transistors. Let me connect it up in unity feedback like that. And apply V bias to that stage, and let us say V bias is somewhere in the middle of the supply. Okay. Let us say VDD by 2. Now, what do we expect if the op amp is ideal? If this is VDD by 2, I would expect VDD by 2 over there. Okay. Now, clearly the currents in M11 and M12 have to be equal to each other. Okay. That is just from Kirchhoff's law here. And also, if this is around VDD by 2 and this is VDD, both transistors will be in saturation region. Okay. You imagine large VDD. So, the VDS of M11 and M12 are very large. So, they will be in saturation region. Now, if the two transistors are in saturation region and their currents are equal, okay, the voltage here will be VGS12, that is required for a current of I12, okay, and the voltage here will be VSG3, that is required for a current of I12. Now, we know that in the balance condition, the differential pair by itself would give you VDD minus VSG3. Okay. The voltage required at the gate of M11 would be VDD minus VSG11 for a current of I12, whatever that is. Okay. We say that the two currents are the same, of course, and they are both in saturation region. Now, the differential pair will tend to give an output of VDD minus VSG3 when it is balanced. Let us say this VDD minus VSG3 is not equal to VDD minus VSG11 required for a current of I12. So, what happens when we connect these two together? The output of the first stage has to move from its natural value of VDD minus VSG3 to the gate voltage required for M11 to carry a current of I12. Okay. So, what I am saying here is that the first stage differential pair would naturally carry some current, but it has to change from there to a different value, which will make the transistor M11 carry a current of I12. Now, how will that happen? The only way for that to happen is for the differential pair to have a non-zero input voltage, okay, because if the input was 0, the output would be VDD minus VSG3. So, this of course means that there is a difference between this one and that one. So, the output will not be at VDD by 2, but it be at VDD by 2 plus some delta V, and what will be the delta V? It will be the change required at the output of the first stage, okay, which is VSG3 minus VSG11 for a current of I12 divided by the gain of that stage, which is GM1 by GDS1 plus GDS3. Please go through the reasoning carefully. What I am saying here is that the first stage has some natural output voltage. When you connect it up in a feedback loop with a second stage, the first stage output has to change, so that the second stage carries a current of I12, which is what is supplied by the current source of the second stage. Okay. And because it has to change, the input voltage of the differential pair has to change, which means that there is an offset. Now, this offset is not because of random mismatch between transistors. This is because output voltage of the first stage is not equal to the input voltage required by the second stage to carry a current of I12. Okay. And this is known as systematic offset, and the way to avoid this is quite obvious. If we make VSG3 equal to VSG11 for a current of I12, then the first stage output does not have to change when you connect it to the second stage and connect it in feedback loop. So, it will make sure that there is no systematic offset. Okay. VSG3 for a current of I0 by 2 is not equal to VSG11 for a current of I12. Okay. This is because output of first stage is VDD minus VSG3 for a current I0 by 2, and the input required for the second stage VDD minus VSG11 at a current of I12. And to avoid this, you make deliberately VSG11 for a current of I12 equal to VSG3 for a current of I0 by 2. Okay. Now, can we do this? We can certainly do that, because M11 and M3, M4 are all PMOS transistors. What we have to make sure is that VT both have the same VT, VT plus square root 2 times I0 by 2 divided by mu p Cox W3 by L3 should be equal to VTP plus square root 2 times I12 divided by mu p Cox W11 by L11. Okay. What this means is, of course, I0 by 2 divided by W3 by L3 equals I12 divided by W11 by L11. Okay. This is usually referred to as the transistors M3 and M4 and transistor M11 operating at identical current densities. Okay. If you make the lengths equal, the width ratio will be equal to the current ratio between the transistor M11 and the transistors M3 and M4. Okay. Now, this is done to avoid systematic offset. If you do not do this, there will be a systematic offset which is equal to the difference in the VSGs divided by the gain of the first stage. Now, it turns out that this is not always possible to do. Sometimes it is not easy to arrange this. So, in cases where the gain of the first stage is very large, the systematic offset will be very small anyway, and you do not have to do this. If the gain of the first stage is modest and you are looking for very small offsets, you go ahead and make the current densities of the transistor M11, that is the second stage transistor, equal to the transistors M3 and M4, and you will not have any systematic offset. The offset will be governed only by random mismatch of transistors in the first stage. Okay. So, what we have done is to take the 2 stage op amp and realize it at the transistor level. It is quite convenient. You take the single stage op amp and follow it up with a common source amplifier loaded by a current source. Very easy to calculate the small signal parameters and noise and offset and so on. Noise and offset are contributed primarily by the first stage, and systematic offset will be eliminated by equalizing the current densities. So, in the next lecture, we will calculate the slew rate, swing limit, etc. of this op amp and compare it to the other op amps that we have discussed earlier. Thank you.